Now, one common challenge to this notion of the prefrontal NCC is that patients with prefrontal lesions don't become unconscious. That is, in the context of visual consciousness, they don't go blind. This question, though, is very complex. First, we have to be mindful that we are not talking about blindness as in lacking the ability to do visual tasks. Based on the logic of the experiments we just went through, prefrontal damage may not change that very much. What it may change is one's subjective report about the experience. A second point is that unilateral damage to the prefrontal cortex often doesn't abolish all the relevant functions. That's because prefrontal functions, except for language, aren't so lateralized. When one side is damaged, the other side can take over. That's rather unlike the primary visual cortex, which is spatially organized. So we may need bilateral lesions. But these patients are rare. Many previously reported bilateral cases turn out not to be truly completely bilateral, and even when you really find such rare patients, they are generally rather impaired, so it may be quite hard to test them. What about lesion animals, you may ask? Well, again, it's not so straightforward, because here the focus is on subjective reports. So we have done a study using TMS, transcranial magnetic stimulation. We used a specific type of TMS called the theta burst protocol, which sends trains of gamma bursts modulated by theta rhythms. This mimics some known physiology of brain tissues during long-term potentiation and long-term depression, that is LTP and LTD. So the good thing is stimulating a brain area this way for a minute or so can lower the activity of the area for up to an hour. So this way we can stimulate both sides of the lateral prefrontal cortex sequentially and expect that for the next hour or so both sides will be affected. You don't want to actively stimulate both sides simultaneously because of the worry that it might cause seizure, but how here we are stimulating sequentially. So what happened when we TMS subject this way? Well, their ability to do simple visual discrimination tasks did not change at all, as expected. What change was shown here? A measure of their metacognition. Let me explain what this measure means. Usually when you do a task and I ask you to report about your conscious experience, on trials when you say that you are consciously seeing the stimulus, you're more likely to be correct in the discrimination task. When you say you don't see it and are just guessing, you are less likely to be correct in the task. So there should be a correlation between the two. Method D prime is basically a measure of that correlation, correcting of numerous factors using signal detection theory. This method was developed by Brian Maniscalco, a student who worked with me at Columbia University. Because method D prime is in the same scale of signal-to-noise ratio units as D prime, which is just a measure of your discrimination accuracy. When you normalize method D prime by D prime, essentially you measure one's metacognitive efficiency. That is, given you have this much information you have for doing the discrimination task, what proportion of that information is available for you introspectively? And this is captured by this metric called the M ratio. As you see, prior to TMS, people were nearly perfect. After TMS though, this metacognitive efficiency dropped by over 20%. And we know this is not just session effects, like people getting bored or tired, because in sham TMS session, we didn't find the same effect. Now then, once you see the logic of this analysis, you see that you don't necessarily have to use subjective ratings of conscious experience, which may seem a bit vague. You can actually ask people for the confidence, that is, how likely they think they're correct in the discrimination task, which may seem like a better defined question that has a clear correct answer. That's what Steve Fleming did for patients with unilateral lesions in the prefrontal cortex. Like I said earlier, because the lesion was unilateral, you don't expect very large effects. But somewhat surprisingly, in fact, metacognitive efficiency dropped by about 50% in these patients. Very importantly, this effect was specific to the perceptual task. That is, when Steve asked these patients to do a simple memory task and do the same confidence ratings, their metacognitive efficiency was not impaired. So we can rule out that it was a general impairment on metacognition, or just something difficult like having to think about how well you do in a task. It is specific to perceptual experiences. Earlier, I said that, getting at subjective reports is tricky to do in animals. It is, but if you can translate the problem into one about confidence, well, then we can infer about an animal's confidence too. For example, we can let them press keys to indicate how much they want to wager on a trial, more food or less food. Or we can see how long they are willing to wait for the reward, which will only come if they get the discrimination correct. If they aren't sure they got the answer right, they may give up rather quickly, rather than waiting for a long time. So these studies have been done in monkeys and rats too, by injecting muscle into the prefrontal cortex. Just as expected, meta D' is impaired, but the primary task performance was unchanged. If you are still not convinced that this measure of metacognition is about conscious experience, even though it's specific for perception but not memory, now, just for another piece of evidence, I can tell you that patients with prefrontal lesions often show conservative bias in detection too. That is, once again, the perceptual sensitivity seems unchanged, but they are more reluctant to report they see something. So overall, I think it's fair to say lesion to the prefrontal cortex does impair some important aspects of consciousness. It doesn't change the perceptual signal itself, but blindsight patients also don't lack that signal. It impairs your own subjective interpretation of that signal, which is also a problem blindsight patients suffer from. Now, there is another common challenge to the prefrontal NCC view, which is that prefrontal activity simply reflects the report of the subjective experience, but not the experience itself. I will address this problem later on when I talk about the findings of another recent experiment, so I will be brief here. Basically, like the problem of lesion, the claims here aren't empirically quite right. If you only look at fMRI or EEG signals, done using simple, old-school data analysis methods, fine. There may be a sense that when the subjects don't make a report or don't attend to the stimuli, these simple activation or ERP measures are very much diminished. But that may just be because we didn't look carefully for any residual activity or use more advanced and sensitive analysis methods. In particular, if you look at single-cell and multi-unit recordings in monkeys, the answer is very clear. Unattended and unreported perceptual content can surely be read out from the prefrontal cortex, sometimes nearly as well as attended and reported content. Some of these studies are reviewed here, so the evidence is clear. Like the lesion problem though, some folks somehow continue to think that this report confound is a damning issue for prefrontal NCC views. But well, some of these same folks also believe that stones are somewhat conscious. So I don't know, maybe we're fine. So let's say the NCC is really mainly in the prefrontal cortex. But why? Why the prefrontal cortex? What does it do? What are the relevant computational circuits? The role of the prefrontal cortex in conscious perception may be this. When you see a duck, you have object-selective neurons somewhere in the temporal lobe firing. But very similar neural activity can be found when you imagine a duck or hold the image of the duck in your working memory. In fact, these same neurons also show spontaneous activity, as all neurons do. Every now and then, they fire for apparently no reasons. But we don't hallucinate ducks because of that. This must mean somewhere in the brain there is probably a mechanism for telling the difference between these different scenarios, given some rather similar visual activity. Let us call this function perceptual reality monitoring. This may be the role of the prefrontal cortex in conscious perception. In fact, there's a fair bit of empirical evidence for that. Earlier we said that the prefrontal cortex is known to be important for perceptual metacognition. If you think about it, that is basically the capacity to tell whether we see something correctly or whether some signal in the visual cortex may just be noise. But what about the other two scenarios? That is, telling the difference between seeing something as existing in the external world right now versus recognizing that the visual imagery is caused by oneself. Turns out there's evidence for that too. Diego Mendoza Holiday has done single-cell recordings in monkeys. In a working memory task, the animals had to remember the direction of some dot motion, holding it in working memory so as to respond later after the delay, to see if the test stimuli matched the sample. There was another very similar perceptual task, which was basically the same, except that during the delay period, the stimulus remained the same on the screen, so there was no need to remember it. The animal could just see the dot motion instead of holding it in working memory. In both task conditions, during the delay, there were neurons in the dorsolateral prefrontal cortex which coded the direction of the motion. But turns out, for the working memory and perceptual conditions, different neurons were involved in coding the direction of motion during the delay. So the coding in the prefrontal cortex could distinguish between seeing and remembering the same content. This is obviously a very good mechanism to have. Without it, one might be in some state of psychosis, confusing imagination with reality. There is also a developmental argument as to how we evolve and grow to have this mechanism in the brain. So we all know that predictive coding is something very good to have. It is powerful to be able to exercise your perceptual representations in a top-down way to anticipate what it is to come, etc. But trouble is, as we learn in modern neural network modeling, like those so-called deep learning models, training these generative models is generally pretty hard. It takes a lot of time and data. There is one hack though, called generative adversarial network, which is what Ian LeCun, the head of Facebook research, calls the coolest trick in machine learning in recent years. The idea is, while you're trying to train the generative network, one that creates detailed perceptual representations based on an abstract concept as input, you also train a discriminator. The job of the discriminator is just to detect if the perceptual representation is actually coming from the real world or is it created by the generative network. So it's a bit like forgery detection. If the discriminator successfully detects forgery, it wins a point over the generator. If the generator successfully gets away with an undetected fake, it wins a point over the discriminator. By pitting the two networks against each other this way, they both grow quickly, like rivaling siblings. Sam Gershman at Harvard has actually written out the math for this, and I agree with him that the discriminator is likely subserved by circuits in the prefrontal cortex. There is a philosophical interpretation of the theory too. In fact, the theory is based on an old Kantian idea and is a variant of what is called a higher order theory of consciousness. So one may expect a theory of consciousness to explain why there is such a wonderful thing as subjective experience which occurs in the first place. But most theories don't really give a very satisfying answer. Perhaps that's because the question is somewhat too hard or maybe confusing or ill-posed. When we say there is a subjective experience of seeing though, what does it really mean? Well, typically it means that when you see something subjectively, you experience it in such a way that there is a strong tendency for you to believe in what you see. The content presents itself to you as if it is self-evidently true. You can override this with some background belief to tell yourself, well, you must be dreaming or hallucinating. But all the same, the experience gives you what philosophers call an esoteric force. In the face of contradictory background beliefs, you don't just let the pieces of evidence accumulate and cancel each other out, etc. Regardless of the background belief, things look a certain way. They look funny even when they make no sense. But that funny look and the esoteric force can't be reasoned away. Just like the way that you can't reason away a headache or a pain in your foot. Which is probably why it seems to make all the sense in the world to believe in what you consciously see. Such a belief seems to be justified by the perceptual experience itself. But as the philosopher Donald Davidson famously pointed out, how can a perceptual experience justify anything? An experience is not like a logical statement. But with the prefrontal metacognitive mechanism, you can see how, together with the first-order perceptual representation, they form the basis of a logical inference. One says duck, and the other said this is correctly reflecting the world right now. So like in a syllogistic argument, you conclude that logically, of course there's a duck, on the assumption that your prefrontal mechanism is reliable overall. So the theory explains the essential feature of subjective experience, which is that they have esoteric forces, something that is lacking in blindsight. Of course, blindsight patients only think that they were guessing. All of this, of course, is not to say that you as a person make these logical inferences with effort. It is a subpersonal process. It happens automatically. So, we have not just the NCC. We also have a theory of why it works this way in the prefrontal cortex. This may become handy when we eventually deal with animals who don't have a prefrontal homologue, or maybe for creatures who don't even have a cortex or even a brain. But I cheated a little. I started by promising to talk about emotions. Experiments with visual stimuli may be convenient, but do they generalize? Turns out it does. There is at least some evidence that the prefrontal NCC works for fear too. There's a study done by Vincent, a postdoc in my lab. Here, subjects in the scanner viewed many images within a single session. The images were mostly animals. Some are commonly frightening, like snakes, spiders, etc. The task was the subjects had to press a button whenever they detected that there was a category change. That is, the new image belonged to a different kind of stuff compared to the previous images, like a change from snakes to rabbits, as shown here. Now, during fMRI scanning, we can record skin conductance as a measure of the physiological response to threat. And before and after the scanning, we can also ask people to rate how much they were afraid of these items. You see that, perhaps not so surprisingly, the two measures correlate. But the correlation isn't so perfect. There are some things that people are more subjectively afraid of than the physiological responses may suggest, or the other way around. So, of course, skin conductance is also known to habituate pretty quickly. So after seeing a few scary things, the response may become smaller, but people may still feel that they're just as frightening, if not more sometimes. This means that we can look at the fine-grained spatial pattern of fMRI activity within the brain region to build different decoders to try to read out the subjectively rated fear as well as the skin conductance response respectively. So a region may turn out to be great at decoding subjectively rated fear, but not so much skin conductance. This was the case for some of the lateral prefrontal regions shown here. Regions like the amygdala, insular, the ventromedial prefrontal cortex, which are traditionally thought to be important for fear, turn out to be better at decoding skin conductance rather than subjective ratings of fear. So this is somewhat similar to studies of visual awareness. There may be first-order regions important for autonomic information processing, but when it comes to subjective experience, as reported by the subjects themselves, the prefrontal cortex may be more important. So earlier we talked about one common objection to the prefrontal NCC, that it may just reflect the report demanded by the task. Like I mentioned, the issue was already dealt with in neuronal recording studies in monkeys. But here, you can see even in fMRI, the activity in the prefrontal cortex does not just report what the subjects were required to report. Here, all they had to do was to detect the category change, and yet we can decode the fear they presumably experienced while seeing these animals too, as given by ratings done outside the scanner. So this also contradicts with the notion that activity in the prefrontal cortex just reflects a kind of global attention state, but has no perceptual content. So even though some of these criticisms continue to be repeated in high-profile journals, we really have to be careful. They're just not empirically true.